From the Library of Congress in Washington, D.C.
Good morning, everyone, and welcome to the 71st Topics in Preservation series. I'm Fenella France, Chief of the Preservation Research and Testing Division, and I'm delighted to welcome you all here today in person. We do have about 100 people signed up remotely. Unfortunately, we are having some problems with our webcast, which we hope to actually start a new session and get them on, because we have someone actually getting up at 2 o'clock in New Zealand. I'm quite impressed by that. So our speaker today is our very own Dr. Eric Breitung. He's a scientist here in the Preservation Research and Testing Division at the Library of Congress. Eric is a physical organic chemist with 10 years of industrial research experience in coatings and thin films. He began working in the field of art conservation science in 2006 as an Andrew Mellon Fellow at the Metropolitan Museum of Art, developing novel methods for treating and producing scratch-resistant large-format face-mounted photographs. Aligned to this was a project focused on novel anti-tarnish coatings for the protection of silver objects, and this developed into an NSF-funded grant with collaborators at the University of Maryland and the Walters Art Museum. He's also studied natural and synthetic dyes and Central Asian ICAT textiles at the Smithsonian Institution, and now focuses on modern materials research, looking at degradation mechanisms both in modern materials as well as the impact and effect of modern compounds and composites on traditional collection materials. Part of that research is developing a paper-based sensor system for evaluating potential preservation materials, and as you know, this is an area of a lot of interest to many of us for trying to protect our collections. The title of his presentation today is Evaluating Storage Materials for Cultural Heritage, Alternatives to that Delightful Oddy Test. Over to Eric.
Let's see how we're going to do this. Okay, as Fenella said, so thank you for coming, and I'm going to talk to you about sort of what the Library of Congress has been doing for just using the Oddy test itself, as well as developing new methods for looking at an Oddy test that might be more appropriate for a paper-based collection rather than metals. I'd like to start out by thanking a lot of people that did the work for this. We're mostly interns, fellows, and volunteers. Marcy Wiggins is now at the University of Delaware getting a PhD in analytical chemistry. She did a lot of the ion chromatography work. Aaron Ullman is looking for a job in forensics. He just got a master's in forensics, I believe, research of some sort, and he's looking for a job, I think, in Ohio. And Linchi Nguyen is a high school student that came to us through the ACS SEED program, who just started at, she just graduated from high school and just started at Princeton a few weeks ago, who did a lot of the mass spec work. Aaron did a lot of the XRD work. And then I'd like to thank Claire from the Conservation Division, amongst the rest of the folks in conservation that talked to me about what materials to test, and Claire did a lot of work to get me those materials. So I'll start out for a basic primer of the Oddy test. I'm assuming most of you know about it. This was developed in the 70s. It looks a lot like this vial over on the left. Oh no, am I going to get this right? Yeah. All right, so the left side where there's a little test tube, you put a preservation material in it with a little bit of water, so there's a small vial of water, and you put metal coupons to see whether those metals will corrode as you age them in an oven over time. The original test had silver, lead, and copper in separate vials. This was then converted to one vial with all three coupons in it. And what we use, and I think what was developed at maybe the Metropolitan Museum of Art, was this jar on the right, where it's a little easier to get things in and out of. And you just fold the coupons and put them over a beaker. And again, look at the corrosion that you see on these metal coupons as you put a preservation material in the jar to see if it's going to off-gas and cause problems with the metal. And we use this as a way to determine whether we should use these preservation materials with cultural heritage objects that are fairly precious. The test has been fairly consistent with using these same metals. Everyone seems to use water, and the idea is to use an airtight container, which seems to be a huge challenge for 28 days at 60 degrees Celsius. And we've stuck with all of that, and then we do a visual assessment of the corrosion, which is incredibly subjective and difficult. We compare it to a negative and a positive control. The negative control is just air in the container with the metal coupons, and then the positive control is something that's going to corrode these metals in a reliable way, which is often either finding something that we've tested that turned the lead into a powder, or maybe some people use actually just certain concentrations of acids, which I've seen in a few papers from Germany. And then we rate them as either acceptable for use permanently in the collections for decades, or temporary, so that means different things to different people, but it's often 3 to 6 months. So you could use some material for maybe an exhibition, but then you'd want to get it away from the object. And then unsuitable is just don't use it at all in the collections. And so a picture of what we use is the jar system. It looks like this. We've added some little glass beads to keep the beaker from moving around inside the jar. The bottoms of our jars are sort of belled, curved, and so the beaker wobbles around, and eventually the coupons touch the edge, causing condensation, and sort of we get false positives where there's water condensing on the metal coupons. And here's an example of a lead coupon that was in with an unsuitable material, obviously, and we would get all 3 coupons. We'd take them out, unfold them, put them in Petri dishes, and take a photo, and also look at them in a true light box, and doing that comparison and ranking. So the question we had was, what is the Oddy test really telling us? What are we evaluating when we see metal corrosion? Obviously something's off-gassing from the preservation material, but what are those corrosion products, and what does it mean that we're getting those specific corrosion products? Is it telling us that it's okay to use with paper collections or not? And so we tried to evaluate what the corrosion products were using X-ray diffraction. And again, this was Aaron Ullman that did a lot of this work as a master's thesis. And we recently acquired a rapid XRD machine for powder X-ray collection. And for those of you who aren't familiar, there's an X-ray tube here, which is also here in this picture. Those get shot through a collimator, and then our sample is right at the end of this little wooden stick. And there's a goniometer that allows it to move the sample around. The X-rays are then diffracted from the sample if there are crystals there, and it hits our detector, which is this black screen, which is a lot like it used to be film, and now it's a digital film, much like a digital X-ray you'd use at a hospital. With the help of Lynn Brostoff, a colleague at the Library of Congress, we developed this method for basically sampling these metal coupons. So a lot of and if you've done the Oddy test, it isn't necessarily true that you get large crystals on all of the coupons. Sometimes it's just a little film or a haze, and so we're trying to get the crystals or any crystalline materials from those materials. And so Lynn had found that by sharpening a wooden stick, so this is a Q-tip, if you can see, it's one of those long sticks we use in preservation all the time, just sharpening the end and then cutting it off to make a small stub, and then just scraping the surface of the metal, that we can get enough material there to get signals and actually see those crystal patterns. And so that's what Aaron is doing in this picture. Is this, I think, is a silver coupon. He's scraping that surface to try and get some of that black stuff that you sometimes see. It's often very difficult to see visually at the very tip of the coupon. That's the part that's hanging inside the jar. And then we mount it into a holder. And the other nice thing about this technique is that once you get the sample aligned, if you can manage to get it approximately the same depth in this holder, which is just being held by wax, then you don't have to do much work to realign it in the system. And so you can really rip through these, because the slowest part is often realigning your goniometer or sample to the X-ray beam. And so with that kind of setup, we get data that looks something like this, where the amorphous stick that we see is this sort of bright area here at the center near the beam. And you can see I've chosen sort of an ideal image here for what data looks like. But that is easily subtractable out of the baseline. So we get a nice flat baseline after doing a background correction. And the data for this is plumonicrite from one of our samples is quite beautiful. You see a lot of very nice bright bands for the diffraction pattern. And then we match those to library spectra and do our assignments of what phases are present. This happens to be a single phase sample. If we had multiple phases, we have the ability to sort of subtract out what we've positively identified and then do multiple phase analysis. So it's quite a nice system. This is a list of some of the materials we tested, both with the Oddy test and with XRD. And basically what we did is looked at a series of different materials that are used in primarily bookbinding. And for the Oddy test, we would just chop the samples up into small pieces. That's easy to do with these binding boards and book cloths. For the adhesives, we would use Mylar and spread a thin film of the adhesive out and then cure it for a certain amount of time. Then try to peel it off the Mylar. For those that didn't peel off, we would scrape them off and use, in each case, I think it's 2 grams of material. So we did foams, adhesives, book cloths, and binder boards. And the X-ray diffraction results showed that we get a lot of different phases of materials. And I'm going to go sort of coupon by coupon. So we'll start with lead, which happens to be the coupon where we always see the most corrosion. It's really the canary in the gold in the mine for determining whether your material is bad for collections, right? And I've purposely made these small, and it's even smaller on your screen here. But basically what I wanted you to see is how many samples showed lead corrosion. There's a lot of them, maybe 20, 25. And that what we see in there is that we see a lot of plumonicrite and hydrocerocyte carbonates. We see a little bit of oxides, litharge and massicot, and not very many carboxylates, which is somewhat surprising. That we don't see, I think there's 1 or 2 samples with acetates and 1 or so with formates. And that if I was going to keep one metal coupon in the Oddy test, it would be the lead coupon, right? And so we asked then the question, where are these coming from? If the control, which has air in there and moisture, doesn't form a lot of corrosion products, so that's what the lead coupon looks like in the control, why don't we see a lot of crystals forming on that? Because you can, in air, you've got oxygen, you've got moisture, you should be able to make lead oxide, and then we've got carbon dioxide in the air. Why is that not forming lead carbonate? So what is it in the preservation material that is providing the bump that it needs to form these corrosion products, and does that matter for our collections? And so you can see that the oxides would be formed litharge and massicot with oxygen, and these carbonates, obviously you need carbon dioxide. But we don't see those in large quantities on the control. So what mechanisms are forming these corrosion products? We basically did literature searches to find what the common belief is on what the corrosion products, where these corrosion products come from. And everyone knows that if you have carbon dioxide and there's water present, that you form basically an acidic solution. We're acidifying our oceans with carbon dioxide. It's the same in the lab. You form an acid or proton that is from the carbon dioxide, and that can further break down into more protons. But that carbonate with a lot of acid in the presence of lead oxide, which we've already seen from the previous slide, can form just in the presence of oxygen, will give you plumonicrite, which we saw a lot of on these coupons. And then if you have an organic acid like acetic acid, that can dissociate, forming protons that can do the same thing. That can feed into this reaction. In addition, the acetate anion can then be used to help form the lead acetate, right? And then hydrocerocyte uses that acetate anion in an equilibrium process to form hydrocerocyte. So in all of these cases, an acid is part of the equation and is key to forming a lot of corrosion. And so most of the time when you're seeing corrosion on lead coupons, it's because there are acids being evolved from your preservation material. Looking at copper, the question is it the same situation? Are we seeing anything new or different when you look at the copper coupon, or could we just look at the lead coupon? And here you see the list is a lot shorter on the right side, that is about half the number of materials that showed a temporary or an unsuitable coupon on the copper. And most of it is tannerite, which is copper +2 oxide. And then there's a few sulfides and one or so formate, right, or carboxylates. We don't see any copper acetate as a phase. And it doesn't mean the stuff isn't there, but if for anybody who's done the Oddy test, you'll know that looking at the copper coupon is very difficult to say, well, this is corrosion or it's not corrosion. It doesn't typically spring a pile of crystals on top of it. It can, but not like the lead. So for this picture here of the Oddy test, there's a big white cloud of crystals on the lead, and there's sort of a haze here on the copper, and so this is likely a temporary coupon rather than unsuitable. So it's harder to judge. And so, and maybe you're seeing why that you don't see as many crystal forms, crystals forming on that surface or corrosion products. So what's the mechanism for producing the ones that we did see? So forming cuprite, you need a lot of acid to form cuprite. So for every couple of coppers that go into cuprite, you need 8 moles of acid to get to that point. So you oxidize the copper, but you need oxygen around and you need acid around to have that happen. And then that cuprite can convert to tannerite. And so what we saw mostly on the previous slide was tannerite, and that's an electrochemical process where acid is also involved in the reduction of oxygen. And so again, acid is a key part of the equation for producing the copper corrosion products we're seeing. So maybe it's giving you the same information that the lead is, it's just harder to read. And then in sort of that conversion to tannerite, these are just some nice schematics we found in the literature to show that process and to form the carboxylates that can also dissolve into the surface layer of water. So I didn't mention it, but basically all materials, and definitely metals, have these monolayers of water or multi-layers, but on the surface. And so the metals are in both the ionic and the metal form on the surface in a small equilibrium for silver, copper, and lead. They're hydrated or have hydroxyl groups on them. And this is where all of these gaseous materials can come in and interact on the surface. So when you see this huge blue area that they've drawn, it's not a lake of water, but there is water on the surface unless you're in an ultra-high vacuum. Right, and so this chemistry can happen on the surface of a metal. They've drawn it a little different here. The water layer is a little smaller, and they're calling it a crack that gets you down to the copper oxide. But then through those processes I showed on the previous slides, you can make the organic acid acetate versions or the carboxylates of these coppers, and their reaction processes agree throughout the literature. So again, for copper, acids are key. How about for silvers? Again, it's the acids. We've got about the same amount of compound corrosion products or coupons that provided corrosion on silver. These are incredibly difficult to see, in my opinion. You end up with these very faint black edges. We always clip one corner of our coupon so we know which side was inside the jar, and you'll see this little haze of black on the edge, and you can say, okay, maybe there's some sulfur in there. But silver, turns out, is pretty stable. When your sterling silver at home corrodes, a lot of that is the copper in the sterling that's corroding, not the silver, to give you the coloration. And here we have 99.99 something 9% silver, and so it's pretty stable. And so you can get chloride formation, you get sulfide formation. We so clearly see these phases here, but you don't get a ton of it. So where do they come from? I think most people know that hydrogen sulfide is a good source for sulfide anions, and it's the same process. You have a hydrated layer on the surface, hydrogen sulfide hits that surface, disassociates, and you end up with silver sulfide. But it was a weak acid that started that process. In the case of chloride, there are many places you can get chlorine anions, but one of them is hydrogen chloride or gaseous chloride gas, and that forms the chloride anion, can then form a silver chloride solid on your surface. So in this case, you're more directly forming these corrosion products from acidic precursors. And so what does this mean for the Oddy test? Primarily, remember that XRD doesn't tell us how much of any of these materials are there. It just says that they are there. So we can't use that as sort of a way of differentiating or taking the subjectivity away from the Oddy test, but it tells us what's on the surface and possibly what's causing the corrosion. And in all of these cases, we found that acids are mainly the material that are catalyzing the corrosion, so that we get a lot more in the preservation material jars than we do in the control, where there is supposedly no acid. We know that if you've done these, the lead is much more sensitive to corrosion than the copper, and the copper is about the same as the silver, it turns out, as far as the numbers that we see that are corroded. And I find that the copper and the silver are difficult to assess visually. For that, people have started looking at silver, and I think people even looked at copper thin films, which end up having more topography, and color change on the surface ends up being a little bit more exacerbated, and so you can see changes more easily. And that work most lately was done, I think, at the Met with Robin Hodgkins, but it was started a long time ago with Hawkins. And we have not started doing that here yet. We need a thin film depositor. And people have attempted to standardize this process, and I'm just bringing this up so that everybody's on the same page of what we're doing and why we're doing it. Back in '95, Green and Thicket looked at 10 labs. They sent samples, the same samples around to 10 labs with instructions for how to run an Oddy test so that everybody did it the same way with 5 materials. And they found that 3 of those materials came back with ranges of permanent to unsuitable. And so it basically said, well, we aren't standardized. And they had reasons for why that might be, that people did the test differently. But likely everybody's doing this test slightly differently at different institutions. And so that's why we're getting different results. And they made these 3 recommendations for sort of standardizing the test. One is to use very pure metals. We use 99.9 or better for purity. We don't use a heat shrink collar, but we go in after our vials have heated up to 60 degrees and we retighten them. And then I monitor those throughout the month to make sure there's still moisture in those vials. If they end up dry at the end, we throw the test away. It's of no use, really. And then, depending on what size vial you use, if everybody uses the same ratio of the volume to the amount of water, then you're more likely to get the same result as someone else. The problems with it is that it may only be detecting volatile acids, and so if that's okay for paper, maybe that's fine. And we're going to maybe learn that in the next few slides. But if you have paper or wood or parchment or organic materials, maybe only detecting volatile acids isn't good enough. And so we then ask the question, is that right? Are metal surrogates okay, or should we go to something that's probably more difficult to assess? And are acids the only harmful agents? And this is where this paper Oddy test comes in. We based our sort of test setup on some work that Dr. Shahani had done at the Library of Congress back in 2001, and as well it's been somewhat adopted here and there. Strelick used something very similar in 2010 for a study that he did. And so what it is a gram of Wattman filter paper at the top, and this is just a few strips of paper that are coiled and sort of they spring and stay in the upper part of the vial. And then we put a couple grams of the preservation material at the bottom. And there's no moisture or water in there other than we pre-equilibrate the vial to 50% relative humidity in our TAPI-controlled room for several days before we seal it. And we're sealing it with a silicone rubber O-ring. We've leak tested these jars. They're not leak proof, but they're the best jars we've got. They're incubator vials, and they do a pretty good job of holding materials inside. But if you were going to run a test for 2 years, you would not expect that the things you started with inside the vial are still there. So this is a much shorter test. Remember, the Oddy test was 28 days. We're at 6 days, but we've bumped up the temperature to 100 degrees Celsius. And what we're looking for is cellulose degradation of that paper. So here's an image of what cellulose looks like. It's basically glucose monomers that are linked together, and those can hydrolyze, break the chain so you have individual glucoses coming off, or monosaccharides. If you hit it a little harder, you can get aldehydes, ketones, and acids out of it. And if you really, really hit it with heat and ionizing radiation and things, you can get a dehydrated, strange structures out of it. And in the literature today, there's a ton of information out there about depolymerization of cellulose. People are trying to do this because it's sort of the green chemistry future. It's how do we make useful things out of something besides oil. And so there's a lot of information out there. We're just a little ahead of the game with trying to break down our paper in the library. Maybe we've got an energy source. So what do we do with this paper once we've aged it for the 6 days? We want to know what's no longer part of that cellulose chain. What have we broken off of it, or what have we added to it? And so our main method for doing that is to just extract into water. We take some portion of the paper of that. I don't remember how much it was, but we take 0.3 grams of the 1 gram, I think it is, and then put high purity water. And we have two methods. We either let it sit and soak, or we pulp the paper to try and get a better extraction. And we've gotten slightly different results from those two methods. What you're seeing here is just a soaking. In this case, we're incorporating less carbon dioxide into the water, and so maybe this is a more realistic picture of the way it should be. You can see they're set up with the least colored to the left and the most colored to the right. And so maybe we can use color or UV-Vis as a way of detecting degradation, but it's not universal. The non-colored ones also have degradation in them. And so we then take these, the liquid part of this, we filter off the paper and inject it into an ion chromatography system. For those of you who aren't familiar, ion chromatography, we use sodium hydroxide as our eluent. That pumps through a very small tubing system. In that system, there's a column that does a separation of these compounds based on how many charges are on each one, as well as a little bit of the size. We can inject a sample into that line, and it hits the column and starts separating based on whatever's in it that's got charges on it, basically. And then when we get to the detector, it's doing electrochemistry. So the only things we can detect must be electrochemically active, either be reducible or oxidizable. And so we aren't detecting everything in there, and we'll see a little bit of that when I go to the mass spec portion of this talk. So here's an example, not the prettiest example, of one of our ion chromatography measurements, but I wanted to show you what just Whatman paper that's been aged in air and unaged Whatman paper look like. We always put a galactose internal standard in, so we have something to compare to. And you can see the red line is the unaged paper. That has some free materials in it that are ion chromatography active. And that's this one, and this one. And those got a little bit bigger in the aging process. And so we are degrading the Whatman a little bit in just having it in air. And I wanted to say, so the conservators that I presented this to a while ago asked, is it a fair representation to use 100 degrees Celsius when the Oddy test is at 60 degrees? And it's a fair question. Shahani addressed this a bit using physical testing, and that's a report that I think is available from 2001 with, I think, fold testing and so on. He was comparing naturally aged paper to accelerated aging techniques and concluded that I think he used 90 degrees Celsius, that he could get the same results using his accelerated aging techniques. And we're sort of following one of his closed vessel methods. So what we did to check was we took one of the foams that we had tested at 100 degrees and put it into an oven at 60 and just took a sample out of a new jar every few weeks and made it about 13 weeks along that process. And if you look at the area percent, where I'll describe what that is, but basically think of it as the area under this peak here, up to about 300% of our internal standard. But at 100 degrees C, it was 1,000% of the internal standard. So if you extrapolate this line out to 1,000%, it makes it to about 85 weeks, which is about a year and a half. And unfortunately, our test file just isn't sealed well enough so that we could actually run it for a year and a half to find out if this does match the kind of is it a fair comparison, 60 to 100? What I like to see, though, is that the spectra or the chromatograms are similar for a 60 degree and 100 degree aging process. It's just that you have smaller peaks at the 60 degree process. So we think it's a fair compare comparison. The right way to do that experiment, maybe we'll get around to it, is to use sealed glass vials where you flame seal them, and then nothing's getting out until you're ready to crack them open and look at the paper inside. And that might be a way to assess the methods. So for the ion chromatography, we looked at even more samples. We've added some glues and foams, but I won't dwell on this. And then to sort of validate our ion chromatography system to see what those peaks might be, we theorized that they were probably monosaccharides, disaccharides, and trisaccharides that were breaking off of the cellulose chain. And I'll describe a little bit about what all this mess is with the baseline. We start with a low concentration of sodium hydroxide as our eluent, and then to clean the column out or flush it out before we make the next injection, we increase that concentration of sodium hydroxide so the signal of the detector goes up. And interestingly, that's when we see cellobiose, the disaccharide, and the trisaccharide. They come out way late in this process. So most of our analysis, we stop at about 22, 23 minutes. Where actually cellobiose in our current setup comes in around there. And so what we see down here in the 7 to 10 minute range are our monosaccharides. And just so what I'm trying to get you to take away from this slide is these are smaller molecules and they have fewer hydroxide groups on them. These are bigger molecules, they have more hydroxides, they're more ionizable. So things you see on the left side are small, fewer hydroxides, right side, more hydroxides, take longer to come out of the column. And so we'll look at some of our test materials and see what kinds of things are coming out when we get to the mass spec. But mostly what we assess are these early eluders, which are probably monosaccharides. We're taking a guess here. We have no way, other than right now anyway, of looking at these and saying we know what they are without doing mass spec. And so early on, we hadn't done that mass spec. We proposed that this was glucose, this was mannose, and this is our internal standard of galactose, which matches up really well, of course. And we think this is arabinose based on that previous slide. But this is the first time I'm showing you one of our conservation or the preservation materials, the blue and the green line, what are typical results you would get. So this is the Whatman control, the black line, and then the blue and the green line are preservation materials, where the blue one looks a lot like the Whatman aged in air, and so you might say that one is permanent. These peaks here and here don't increase, whereas this green one we might say is not good for preservation materials, and because those peaks grow, right? And so how do we do our assessment in a more, like, not quantitative, but controlled way, I guess? We've decided, to always inject an internal standard. We use galactose, and then we also put cellobiose. It comes in out here somewhere. And we typically look at these three peaks, A, B, and C. This one we think is glucose. We think this is arabinose, but we don't know what C is. And then we look at the area of those peaks relative to the galactose internal standard. So we're dividing the area of the peak by the area of the galactose peak. So if the number is less than 100, then the peak is smaller than the galactose peak. If it's larger than 100, it's bigger than the galactose peak. Then we say, okay, how do you say it's temporary, permanent, or unsuitable for use with collections? And this is arbitrary, just like it is with the Oddy test, except now we have numbers to look at. And so we arbitrarily chose less than 2 times area of the test material peak relative to the, we're calling it a blank, but I meant to put control here. And then if it's between 2 and 3 times the control, we would call that temporary. And if it's more than 3 times the size or the area, then we call it unsuitable. And that's, it was totally arbitrarily chosen, and later you'll sort of see whether that kind of works or not. So let me show you a few examples of the results that we've gotten. This is a binder board that we've aged. The blue line is the binder board, the black line is our control, and here's our Oddy test result. And you can see that these are nearly overlayable spectra, or chromatograms, sorry, where you do the math of how big these peaks are relative to the galactose internal standard, which is what these percents are, and they're very similar in all cases. And so we would say this is less than 2 times the size or area of the control sample, and so these are permanent, or you could use them with the collection. And again, the Oddy test shows the same thing. You don't see any corrosion on these coupons. So here, this is a good match for the Oddy test. In this case, where we're looking at a book cloth, you see, I think this is probably the one I showed you earlier, where these peaks get much larger. whereas C doesn't. You don't see any change. But much like the Oddy test, if any of the chromatogram peaks are larger, we would say that, like, so if one of the coupons is considered unsuitable, or any of the peaks are larger than the control peaks, then we would say it's unsuitable or temporary. The whole sample is unsuitable or temporary. So in this case, we look at these two. They're definitely larger than the control. This one's more than 3 times. This one's slightly under 3 times the area, whereas C is essentially the same. So the IC result is that it's unsuitable, and the Oddy test, maybe not obvious from here, but there's some corrosion on the lead that was more significant than the control, and so that was a temporary or permanent, but not a lot of corrosion, right? So it wasn't unsuitable. And so we have an opposite result, where you might say that typically you would say, okay, sure, let's use this temporarily with the collections, but by IC, I would say don't use it with the collection. This is clearly degrading the cellulose, right? So this is not all the results we have, but a smattering, an example. It's not incredibly biased. We did find that the Oddy test and the IC test in the green, this is the Oddy lines and this is the IC results. The green is showing when they matched. We got unsuitable for one, we got unsuitable for the other. And the red is showing when they didn't match. And there was that trend. There were fewer that didn't match, but enough that were the case where you would want to ask that question, should we be doing some other test? We get enough of them where, here you have something that's borderline great, and it's showing unsuitable with the Oddy results, and maybe we could use that with paper collections. And here you have, there's one where it's the other way around, where it's the IC said it's unsuitable, and the Oddy test said it's temporary or permanent. And so that's when everything looks great on the chromatogram and we know how to interpret it, or we think we know how to interpret it. We got several that gave us stray large peaks, much larger than the peaks than we ever saw coming out of the 3 that we were analyzing for. So in this case, a millboard was showing a very large early eluting peak. And in the case of Plastazote, we got lots of peaks initially that were large, and then an enormous peak overlapping where we were analyzing. Again, we don't know what that is, what that peak's supposed to be, and we're theorizing that these are monosaccharides, but we don't know what these early eluters are. In this case, if we just analyzed using the method I showed you before, we would say this is permanent. Go ahead and use it. It doesn't seem to be degrading the paper. In other words, if these are the only paper degradation products that we're seeing, it doesn't seem to be doing anything to those. So what's happening? Is this just something that's absorbing into the paper and sitting there and then maybe slowly evaporating, or maybe sitting there not doing anything, acting like a sponge but not affecting the cellulose structure? In this case, something is clearly affecting the paper if these are monosaccharides. And who knows what this is, but there's a lot of it in the paper. And so now we have the question, is the paper acting like a sponge? Is that okay? What materials are okay to soak into the paper and what aren't? Or is both happening? And I think we have maybe both cases here. And I know that jade has been a topic of conversation on some forums lately, so I thought I'd show you that one. When we did the jade it cured for 31 days, it showed lots of new peaks here relative to the control, and we got an enormous initial peak plus another one. So we would say that this was, I believe I say it's unsuitable by the IC, and we also found that our Oddy test gave a lot of corrosion on the lead sample, which looks like a copper sample actually, but it's lead. And so now we ask the question, can we assign any of these peaks to find out whether it's reasonable to ignore them or that we have to account for them? And so we also want to make actual assignments of these peaks. We're taking guesses based on retention time at this point. Can we do anything to assign them? And so mass spectroscopy was our next best option for this, where we have 3 ways of looking at the materials that are off-gassing from these preservation materials. And then we also wanted to look at what's actually just going into the paper. So we can look at just what's off-gassing from the preservation material. This would be the third one, the headspace of just the preservation material. This is a SPME fiber, which is, I'm not even going to try and remember what it is. It's a needle, and then there's a polymer-coated fiber that you can hover over the preservation material that either absorbs things that it likes or it doesn't. They come in lots of different forms, lots of different coatings on them. system. We use 3 of those that are typical and used in our field a lot to do both of these SPME measurements. So this would tell us maybe what's coming off of the preservation material. It doesn't tell you what's actually absorbing into the paper or affecting it, but it tells you what might be going into the paper. This one is our water extract, where we're dipping those fibers directly into the water, and this turned out to be a very useful technique because it directly relates to what we're injecting into the ion chromatography system. So we just basically take the fiber and let it sit there for 30 minutes, and then you can inject it into a mass spectrometer and see what's on the fiber. And then because what might be going onto this are those sugar molecules, those might end up on the fiber, but if you put those into your mass spec, they don't make it very far. They're not very volatile, and they're kind of what we call sticky to the column. And so they're likely just sitting at the beginning of the column and plugging it up. So we need to do something to those sugars to get them to go through the column of our mass spectrometer. And that would be to dry. This is the second method, evaporation and then functionalization with trimethylsilylating agent. And so what that does is we allow these samples to dry. The ideal is not to heat them. We only had this as an option. We could have used vacuum, but it would have taken a little too long, I think. So what we did is just blew compressed air over the top of the samples and heated them to 70 degrees at the same time to drive the water off. We're likely driving off any of the volatiles that are there, but we all know that the sugars aren't very volatile, so we think that those would be left behind. And then we take those dried vials, add some other materials. I'll show you how that works. And then we functionalize any of the functional groups that look like this, OH, NH2, so on, and replace one of those hydrogens with a trimethylsilyl group, which then makes it much less sticky for our analysis system. And so let me show you some of those results, just a couple of case studies rather than going through all of them. But the question is, can we identify any of these peaks, any of them, including this one from the archival board using these techniques? So if we do the SPME of the liquid extract, so that was just dipping the fiber into our water extract, by looking at a Plastazote foam, we found lots of stuff: fatty acids, ketones, aldehydes, alcohols. And in the purity of looking at just what those peaks are, we'd say, well, which ones of these are active in the IC? But really, we should be asking the question, are any of these acids, ketones, aldehydes, alcohols, are any of those problematic for preservation? And if you're trying to come up with a standardized test, we always run into this sort of roadblock where you might say, well, yeah, I found oleic acid, but how much is there? So then you need to be able to quantify how much is there. It becomes quite onerous to get to the point where you could say you have enough there that it's a problem. And so that's sort of the beauty of the Oddy test, or even this paper version, that you can say, well, I'm degrading some material to the point where it's visible by a particular technique. So we're degrading paper or we're degrading metal, rather than using mass spec, where this might be trace amounts of these acids, and that's fine. Like we can't assume that anything that's produced that we would use with preservation is completely and totally has no volatiles coming off of it that might harm our cultural heritage objects. So in this case, we don't think we can see acids or ketones in the IC, but we think we can see aldehydes and alcohols. And so maybe these materials, these aldehydes and alcohols, are these peaks. But dimethylbenzaldehyde and phenol are not very large, and they don't have that many ionizable hydroxides. And so if anything, they might be these peaks down here. But they're definitely not this peak that comes way down where Cellulose is near. So this is Cellulose. It's near this. So that's got to have a lot of ionizable things on it, and it's probably larger than the aldehydes or alcohols we have identified. So what else can we find using our other techniques that I showed you with mass spec? So that drying of the sample to look for the sugars looks a lot like this, where these actually should have caps on them. We dried the samples out, added some acetonitrile, toluene, and power sil prep. The power sil prep does the trimethylsilylating. We incubate it for 15 minutes at 70 degrees Celsius, and then inject it into the GCMS. I'm showing you here some standards that we ran, and we didn't identify like glucose. What we identified were by injecting a vial of glucose using this process, we saw peaks that related to sugars. And so I'm just labeling it as glucose rather than showing these complicated structures. And all of these had trimethylsilylated groups wherever there was a hydroxide. We did that with glucose and galactose. We haven't gotten around to doing arabinose and mannose and so on. But this solution in particular had a mixture of mannose, glucose, and galactose. So I know this peak comes from mannose, but I don't know that mannose doesn't produce these other peaks at this point. That said, we get some nice separation, and we can use the retention times when we run this, run other samples, and very consistently get, if we get a peak at the same exact point in the delay of the column, we can say that it was glucose. Whereas if we got this one, we wouldn't know if it was glucose or galactose. And so if you look at Plastazote, what else can we learn using these techniques? Can we identify these peaks? And the answer is yes, we think there's glucose and galactose there. The galactose, I'd hate to say, might actually be our internal standard. It looks like, I don't know if this was aged and then we used the vial that already had the internal standard in or not. But that's sort of not the point. The concept is that we can identify these sugars and say eventually what these other peaks are. And in our case, glucose, again, makes sense. It would be an obvious degradation product of cellulose. And then looking at all those results together, the two methods that we used, one of the other things we found with the trimethylsilylation was a trace amount of maltose. Maltose might actually show up much later. It's got a lot of hydroxides. It looks a lot like cellobiose. It just has a slightly different linkage between two sugar molecules. And so this could be maltose, but if you look at the size of that peak and the fact that we only saw a trace amount in the GCMS, it would surprise me. That said, for all of these identifications, we need another level of confidence to say that there really are those peaks by buying these standards and running them through the IC. So we've gotten all these results in the last month or so and are now in the process of buying these standards and injecting them into the IC to see if they come out at the same place that we see these other peaks. And so sort of that whole point, to remind you, is that we're asking the question, if you have this preservation material, I think this was Plastazote, is it okay if you have glycerol in that system that came from not the degradation of the paper, but just coming from the Plastazote, or maybe maltose, which clearly didn't come from the Plastazote, that's falling apart maybe from the cellulose itself. So we would or wouldn't use these materials or use these peaks as identifiers for problematic chemicals that we're finding in the paper sensor. For the Superior Archival Mill Board, we did the two tests, where here we did the third one of looking at the headspace and the aqueous extract. For the headspace, where you've got the vial of just the preservation material, you're looking at the off-gassing materials above it, we found a fairly large peak of pentanoic acid and then a lot of long-chain hydrocarbons. Neither of which should show up in our IC. So neither of those are likely this very large peak. And so then we looked at the aqueous extract and found these compounds. Note that I'm sort of cherry picking compounds from these mass specs. The mass specs are complicated, and getting accurate identification of the peaks would take a lifetime if I looked at all of them. I'm using a library to assess my results and taking things that have a high confidence of identification using those libraries, and that sort of makes sense with the materials that I'm looking at. But we found pyridine, furfural, phenol, and acetic acid. Again, the acid we don't think we'd be able to see in the IC, so that's probably not this peak. Furfural and phenol might be, and those are small and don't have a lot of ionizable features, so they should come early. So maybe those are what this peak is. Again, in order for us to really say what it is, we need to run one more test by buying those compounds and running them in the IC. And so I mentioned before that the solutions are colored, and I want to finish up with saying, well, gosh, we did a lot of work, spent a lot of time, spent a lot of resources using chromatography, which is expensive, resource heavy, requires throwing away a lot of hazardous materials and keeping delicate pumping systems operating. Matter of fact, I came in this morning and my IC was beeping and saying that it had either a leak or was overpressure. So this is common, and so if we could do this in the field with some other method, we would, right? Especially something that was simple like spectroscopy. And I'm not the first person to mention this. Other people have been trying to relate spectroscopy to the physical methods or physical measurements that we're making, including gel permeation chromatography, pH, and so on. And so there is literature out there that suggests that if you age paper in closed vessels, that's what this V is, that you can increase the UV absorbance of that paper. And this is a high cellulose content paper with no lignin that they were looking at. This is not my work, it's from the literature. And so we said, well, maybe this is possible, that we can just take UV-Vis of these paper strips and correlate that to degradation, so we don't have to do all this extraction and all this physical work that's very time-consuming. So we have a simple, low-cost system. This is, I think, $5,000 to $10,000. I don't quite remember, but it's cheaper than an IC or a mass spectrometer, where you get UV visible light out of one of these fibers. It reflects back in through the fiber to a detector, and you can get a UV-Vis absorption curve. And so what I did is I took a few of these and overlaid them. And the red, yellow, and green, I just highlighted as there. Either if it's red, it's unsuitable, green, it's permanent, and yellow is unsuitable, and ranked them according to the way we rank them using either the Oddy test or the IC test. So the first one is a plot with the Oddy test as the way I ranked these. And you can see that there's sort of no trend, right? You would expect the black line is the UV absorption of Whatman aged with just air, so it's our control, and then the rest are samples that we aged, or sorry, preservation materials we aged with Whatman. And there's sort of no trend when you use the Oddy test results. Whereas you see a trend when we look at the IC test results, and this is pretty clear. It doesn't mean that we could use this and wipe away use of the IC. And I think I'd love for other people to do the same method and see if this works and is repeatable. The black line is clearly down here at the bottom. And you can see that there starts to be a separation when you get to the unsuitable. We're not separating the temporary and the permanent ones down here, the yellow and the green, and there's even some overlap of an unsuitable compound, right, or preservation material. So what I'd say this might be useful for is saving time. So the first thing I would do after removing these from the oven in the future is take a UV-Vis of it and overlay it on this plot and see where it lies. If it has a very large UV absorption or it's yellow, then I don't need to run an IC. I don't need to spend the time extracting it. I can just say this is likely a very unsuitable material. If it's down here, but maybe below 0.25 for the biggest absorption in the UV, then I need to do that extraction to see where it lands using some other technique. And so in summary, we've sort of looked at the Oddy test, shown you how we're using it at the Library of Congress. Maybe said something obvious, which is that lead seems to be much more useful to look at than the copper, and might be showing us very similar information. Silver corrosion I find to be difficult to visually detect. Using our X-ray diffractometer tells us a little bit more about what's actually on that silver coupon, and maybe looking at thin film deposition or thin films as our sensors for that is a good idea. The Oddy test is a reasonable screening method for metals, but you have to be super consistent about the way you run it if you want reasonable and useful results. But it's probably not ideal for paper-based or organic-based collections. We've proposed sort of using this Whatman paper at the library as a sensor. The time for testing is 6 days rather than 28, so that helps. But the way we assess it takes a lot longer. I can rip through 50 Oddy test samples in an afternoon by looking at them, but I can't do that with an ion chromatography system. I can do maybe 6 to 10 in a day if I'm lucky. And it takes me all day. So we propose UV-Vis as sort of pre-screening, so we don't have to do as many of those. And again, that needs to be sort of corroborated with a lot more data, but we so far like what we see. And the ion chromatography with amperometric detection is good for detecting cellulose breakdown products, and gives us a less subjective way of ranking our test results. We've also found that these gas chromatography techniques and methods are great for identifying what those peaks might be. We've got a little bit more work to do to get to the point where we can say which peaks we should really be paying attention to, and what process we might want to use as sort of a standard operating procedure for what tests we do when, and assessing a material for use in collections for very long term. And finally, I just want to thank all the work that the interns and fellows and volunteers did, which have got a lot of this data. The Conservation Division, Claire especially, for providing all the materials and support, and then Cindy Ryan, who helped me with some of the Oddy tests, Lynn with the XRD and the sampling methods, and Jeanette Adams for some consulting on the mass spectrometers, and Fenella for her support of the project. That's it.
So thank you so much, Eric. First of all, I just want to thank everyone who stayed with us and joined us. I know we lost quite a few people, but we did get some up on the webcast, and that will be up on our website, hopefully within 2 to 6 months. You never know, we might shut down. I'll hand over to questions to Eric, and Eric will repeat your question so we can capture that on film.
Hi, John Beatty, Johns Hopkins University. Thank you for a very clear and very informative talk. I really enjoyed listening to it. I have some residual concerns about these tests being performed at 100 degrees Celsius. You did mention the burden of proving that what you're observing at 100 is continuous all the way down to ambient, and I'm not going to dwell on that except to say that you have to prove that for each process, each chemical process. So that's one thing. But what I'm most concerned about is 100 degrees Celsius and the vessel failure. Because you had mentioned with the Oddy, I think you said that getting it airtight is a huge problem, and that's 60 degrees, 100 degrees. How much bigger is that problem? And you have an additional problem, and that is that your feedback that you have with the Oddy, that is the loss of that moisture, you don't have that piece of feedback. We found that when we did put moisture in at Johns Hopkins, we found that all of our vessels were actually failing, whether or not there was a visible indication of it, or whether or not that's the case. Now, we understand that if you do have moisture at the same temperature, you have saturated steam pressure. We corrected for that. But in any case, my question is really, why wouldn't you go a little bit lower than 100 given all these problems?
Yeah, so the question is, there are two questions. One is the 60 degrees Celsius for the Oddy test versus 100, and sort of proving whether or not we're looking at some reasonable amount of a reasonable degradation that extrapolates back down to room temperature. Is that right? Do we have a good way of proving that? And then secondly, if I get this correctly, why wouldn't we use a lower temperature to assess these materials that way we don't have to worry as much about vessels and loss of moisture in the process? Both good questions. The first one, proving that 60 and 100 are the aging we're getting is similar. I recognize that the slide I have on that doesn't show that equivocally, but I would say that a reasonable response is we started out at 100 and we stuck with it. If we're willing to age for a month, you can definitely lower it. And so doing the test to say maybe 70 degrees or 80 degrees, because paper is more stable than these metals, than lead, for instance. So that's why 60 degrees sort of works for making it so you only have to run the Oddy test for a month, right? But if you want to run for 2 weeks, you can lower the temperature. Maybe it's 90 degrees. So I think those tests could be done, and we could figure out what a reasonable temperature is. I agree that 100 is really pushing it. As far as the vessels go, and knowing whether there's moisture there or not, we don't have a good way of knowing that. We know, though, that the vessels we use for our Oddy test, which is that little jar, has a Teflon seal, is just not that good. We know that that's a leaky. If we do a helium test where we fill it with helium and then try and assess how much helium is coming out at temperature, it's like a sieve. Whereas with the silicone rubber O-rings, we do pretty well. It doesn't show these huge spikes of helium flowing out. Helium is tiny, and so it's going to come out of nearly anything unless you have like a metal-to-metal seal that's awesome, right? And so we know there's some leaking out of those vessels, but we think we've got a pretty decent system. That said, if I was going to leave those vessels in at 100 degrees for months, I wouldn't trust it, right? So you know that things are leaking in and out. But aside from doing flame-sealed glass, you're leaking out of any vessel that you have. And you can't use a metal can because the metal can reacts with whatever you're trying to test. So there's a middle ground you have to get to. And it might be lower temperatures, as you suggest, and longer times. But we could also consider adding moisture to these vessels and having an indicator that it's either there or not. There's no harm in that. It might get similar, I assume you'd get pretty similar results. Yeah.
Nebraska, from the Library of Congress. I have actually two questions. So the first is about the Oddy test and the copper coupons. I think your conclusions are good. So I think it doesn't really matter, but I just, about the explanation of the mechanisms on copper, I would question, because two things. One, I think tenorite, even though if you look at a phase diagram, looks like it'll form, it's pretty well known that you need heat to form it. So that could be an artifact of the Oddy test using heat. And the second thing is that copper will form cuprite like in very, very thin film on exposure to air very rapidly.
Right.
So you don't necessarily need an acid, and it's very protective. So I think, I've never understood why the copper coupons were in that Oddy test anyway. I think that they're probably a bad test subject, which you've noted as well, but you really don't see them. So,
go ahead.
Well, I just want to, the second question, so I think it's really great that you're looking at the UV-Vis, and I hope you continue that. And I'm wondering a couple things. First of all, that I know that paper, and I was a little at odds with that paper because all of the guys' interpretation about what's going on in the UV had to do with oxidation. And I mean, really what you showed, or at least what you've been able to detect, has more to do with acid hydrolysis and products, and actually that also corresponds to the Oddy test. So in a way, I think your results are kind of biased towards acid hydrolysis. And I'm not sure how you'll relate the UV-Vis, especially in the UV area, to just, I'm not whether you're seeing oxidation, which you probably won't see in paper unless you have something like iron or transition. I mean, it's hard to cause oxidation in paper, right? Yeah. And I think that all of that is just, something to, you've probably considered some of this stuff already, but it would be great to understand the UV-Vis of the paper better, and maybe incorporate the visible as well, because we were talking about yellow. If the paper looks yellow, then that's actually in the visible that we see something, and that's not visible in those Kubel-Monk transformations that you showed, but rather in the way that when we usually take a visible spectrum. So, sorry, that was a lot.
She didn't ask any questions.
Yeah.
All right. No, I'm kidding.
I guess I'm wondering your response to those thoughts.
So for the UV-Vis, so Lynn asked if, let's see, the UV-Vis, the people that wrote the paper that I referenced talked a lot about oxidation, and those being, they really tried to separate out what was causing each of the rises or peaks in the UV, and attributed a lot of that to oxidation, yet a lot of what I showed was acid hydrolysis. I don't necessarily know that, I believe their results. I did a lot of computations, and I haven't had time to assess it, right? But what they did show was that they had an increase in UV-Vis absorption, or UV absorption, as they aged in different vessels. And so that's what I was trying to show with that slide. Not that they necessarily had the right mechanism for what was causing that. And so I agree that if we want to understand what's happening in the UV-Vis, we have to do more digging to understand what actually causes those changes. For the yellowing, even just a very slight tail of those absorptions into the yellow will give you a yellow paper, right? So the majority of the absorptions are really down in the UV, and then just a slight tail into the yellow region, you'll see yellow. Then the first question was, or comment was about the copper coupons. and the mechanisms that I showed. I agree that those may not be the full mechanism. One thing we do observe, though, is that some materials, or a lot of them that we chose were temporary or unsuitable, produce more corrosion than the control sample, right? And so something is catalyzing a little bit more corrosion. Still difficult to observe. And so, yeah, should it be there? I don't know. I think paying a little more attention to the materials that we're seeing and making those comparisons. Do we really see more sulfides there than we do even with the silver? Is it useful for that reason? It's not, obviously not useful for detecting acids. The lead is the canary for that. So, yeah, I agree.
Can we just take one from the
Sorry.
question?
Oh, yeah, sure.
Just before we come back to the audience, we had one from an external viewer, which is whether the Library of Congress will make the testing results of the specific materials linked with the manufacturer publicly available.
I'm going to let Fenella answer that question.
I was going to defer. So, short answer is currently at the library we cannot specifically endorse specific manufacturers. We are happy to talk with people offline about our specific results, but yes, we will be generally making our results available. And I think most of you know that if you look at MSDS sheets and the types of materials that are present in some of these, you can make a fairly good estimation or guesstimate of what we're sharing with you. Jeanette?
Jeanette Adams, Preservation Research and Testing. I really like how well the UV-Vis work correlated with the IC work. I think that is very, very useful. A couple of things, and part of this goes back to the questions of John. There was a paper published several years ago that evaluated these issues with the Shahani accelerated aging test in terms of vessels. And so there is literature out there documenting that. The other thing is Shahani showed that his aging test, this is in the 2001 ASTM, big huge CD, showed that his accelerated aging test, which uses your conditions here 100 degrees C, correlated very well, almost gave identical data to the natural aging, which was done over many, many years. So I think that's a really good method that you're going with there. The one thing I was wondering about, though, and that's when I was looking at the UV-Vis data compared to the IC data, where it's kind of hard to tell where the data, where some of the borderline ones actually are good or bad. Wattman is so stable, and I was wondering back again to the Shahani work where they looked at a lot of the different ASTM papers, the ISR papers, if it might be possible if you used a less stable paper that could actually in itself basically accelerate the decomposition, that you might increase the yellowing and actually maybe be able to separate out those borderline ones. I mean, some of those, I know we have those ISR papers here, but there's probably comparable ones also out there in the European Union and elsewhere that, you know, this might be a really useful method across the board if we could get a slightly less stable paper, but I don't know. What are your thoughts?
Yeah, so Jeanette's comment is that the Wattman paper is very stable, which is true. It's basically just cellulose. And that there are other standard papers out there that have been shown to be less stable. Maybe those would be better sensors for making this a test that doesn't have to be run at such a high temperature possibly, as well as showing better differentiation of the temporary and permanent materials that we using UV-Vis. And I agree with you. So again, we started early on, we wanted a material or a paper that was easily accessible and well characterized basically, and we went with Wattman. But there's no reason we couldn't put multiple different types of strips of paper in there as well, right? And so we could continue using this method if we wanted, and then put something in there that, just like you have in the regular Oddy test, have other materials, as long as that doesn't break down the cellulose. So we'd have to run some tests to see whether that's reasonable or not. But it's not a bad idea at all. Yeah.
Dana Hemingway, photo conservator here in conservation. I wonder if it's possible to use other detectors like gelatin that would be used in photographs.
Mm-hmm. Sure. She asked if you could use gelatin. She asked if you could use gelatin as a sensor for this. And I think the answer is you can use anything that degrades, right? And so if you have something specific, a material or an object that you're trying to mimic, we can come up with things that are well standardized, that we can characterize fully, and then you look at the degradation products of it and see how much it's absorbing of what's off gassing for your material. So it all just turns into a year-long project, right? Yeah. Yeah. Oh, sorry.
This will be quick. John Beatty, Johns Hopkins again. We're talking about potentially the interpretation of this and pointing us to acid catalyzed hydrolysis, perhaps more than it should. And then maybe you went through this very quickly on a slide, but just putting the Whatman paper there alone, did you, without any preservation material, did you observe any glucose silibiosilitriose? Because HP, high performance anion exchange chromatography, pulse diaphragmatic detection, so sensitive. I would have thought you could see some of those small sugars.
Yeah, so I think the first example IC chromatograms, one was unaged Whatman paper, and the other one was aged for 6 days at 100 degrees C. It was sort of an ugly looking chromatogram. That was what you're talking about, and there was some, what I think was glucose present. I won't go as far to say I saw cellobiose, just because I don't know, and it wasn't on that chromatogram that I showed. But yeah, you definitely see some degradation of the Whatman, and that amount of degradation is fairly consistent. And we use, when we're comparing the glucose peak, for instance, we compare our preservation material area under that peak to the amount that we get consistently from the Whatman at the glucose retention time. So, yeah.
Henry Duan from National Archive. I have a question. I didn't quite catch. The UV study is based on the solid material itself or extractive solution?
Sorry, yeah, that was UV of the paper itself. So
directly on the paper.
Directly on the paper, yeah. And having seen, when I did these slides, actually, I was like, why aren't we looking at the extract as well and doing transmission UV-Vis of the extract? We should probably do that as well. But the data I showed was all direct reflectance, absorption, spectroscopy of the paper itself.
Have you tried other instruments to directly examine the solid state paper itself?
So you asked he's asked if we looked at the paper itself in any other way, and the answer is no. The one test I would love to do, we're just getting going in our lab, is gel permeation chromatography, which also requires dissolving the paper. But that would tell us if we're breaking these chains in half and still making very large chains of cellulose and breaking it down, but not just popping off a single sugar that we can observe. And so that would be our next step if we were to look at the paper, I think, is to do gel permeation chromatography.
No more questions? So just a few things I wanted to note. As you see, we're all just so focused on trying to find a way to predict what's going to happen to our collections and actually preserve them. And so this is really, a way of moving that forward a little bit. I like the comments about the standardization of the paper, or different paper types and materials to be specific to the materials. And just want to note that that has come up in a number of areas. Jeannie Drews, the head of Binding and Collections Care, is working on an ISO standard of a different paper type for Mass D testing. And we also, you may have seen in the slides at the beginning, we've been working on a collaboration with the University College London. We have a doctoral student who will be starting with us hopefully in a couple of years, looking at near-infrared spectroscopy of linking properties and what's happening with damage. So that's something we really hope to work with and look at the flow, how that can tie into our collection. But if you could join with me again, Eric just came back from holiday. It was a brutal re-entry into the real world. I want to thank him so much for such a wonderful presentation.
This has been a presentation of the Library of Congress. Visit us at loc.gov.